Okay. So remember before the midterm, right? Before the midterm, we studied on causal inference on the experiment, but now we want to move on to the observational studies. The problem is that we don't really randomize, right? The treatment assignment is not under our control, right? It's so we don't really have a control over the treatment assignment. It's actually their own choice, according to their own choice. So we don't know how they choose t equal 1 versus over t equal 0. So that means individuals who receive, so on the other hand, on the completely randomized experiment, that means it's a completely random, right? Then basically we know that two groups have no systematic difference. The only difference in their outcome is probably due to the treatment only, right? Treatment effect, because other things are all equal, basically on average. So on the complete randomized experiment, that's nice, but now we have a complication because some x, right? So t and y, some x may may influence both x and y. I mean both t and y, and so that means there could be some systematic difference between the two groups, and so we need to control on x, right? So we want to use the control x to use x to control the systematic difference. So if the variable is related to both t and outcome variable, then it is called the confounder, right? And there could be several confounders. But key idea is, okay, if the confounding variables are known, then within the group with the same confounders, the choice between between t equals 0 and t equal 1 could be viewed as a completely random within that group, right? If you key idea is, on suppose we have a control on all the confounders, then the only difference between the two groups is purely random. So that is the key idea. So that is the assignment of the treatment is effectively and random for the individuals sharing the same confounders. So then we can say that this is this conditional independence may hold if we control on all the confounders. So that means that we need to assume that to begin with. So that assumption is called no unmeasured confounders assumption. So the auxiliary variable contains the individual characteristics recorded in the observable data and available to the data analysis. In general, there is no guarantee that all the confounders are included in X. So we assume, okay, so that's the assumption, is that we are able to, so basically X contains all the confounders. That is the big assumption. Okay. And the problem is that it is impossible to verify this assumption from the data. It's just that you have to believe it. And this is a joint, right? Jointly, so this is about the independence, conditional independence about these pairs. But in our purpose, this is, we don't really need that assumption. We only need this assumption. So this is weaker. And also in other different areas uses different term. So in epidemiology they call it unconfoundedness assumption. In econometrics or some social science, this kind of assumption is called selection on observables. So that means selection mechanism. So this T is the indicator for the selection, is based on the observable, what can be observed. Okay. What's going on? Okay. So graphical, so this is a graphical expression of the same conditional expectation. So this conditional expectation, I mean conditional independence, can be represented graphically as like this. So that means S can explain Y, a T, and Y, T. But they are, so there's no, right, no line between T and YT, right? So that means, after conditional on X, they are independent. But unconditional, they could be related. Okay. Here's an example. Suppose we have a potential outcome model is something like this. Just a linear regression. Okay, they could be different slope, right? So you can have so x1, x2, and and e1, e2 is just the model error, and we allow that these errors can be correlated. Y1 and Y0 could be correlated. It's okay. The only thing is that if the mechanism, selection mechanism T is based on this mechanism, so that means this some function of x, function of x1 and x2 and u, but this u is a purely independent of. So important assumption is that u should be independent of this error. Okay. Then conditional independence holds. Okay. Why? Because what you want to show is that we wish, so why? Okay. Maybe you may wonder, how can you show that, right? How can you show that T is conditional independent of y1 and y0 given x? How to show this? Well, maybe here's something like this. So one way is we want this conditional. So this guy, okay, is a, so this is one, right? So one is a, you know, so that's the definition, right? Conditional on x is a dependency on t can be removed, right? So another way, this is actually equivalent to y, oops, t given x and y0 and y1. Okay. That's another way. So, so either way is fine. I mean, either, so this is another, example. But I guess in either way, so how can we, for example, what is this? Right? For example. Well, this is integration of this conditional, right? Something like that. So this is basically, this is a regression model, right? This regression model. Okay. And this is what? This is the mechanism. So because t is a function of, right? So t equal 1 if and only if x, right? X1 alpha 1 plus x2 alpha 2 plus u equal to 1, given the same thing. Okay. And then conditional on, right? Conditional on x and others, this guy can disappear, right? Because we know that this guy is a function of x and u is totally independent of this y, right? So that means you can actually safely assume given x. So that means this guy is independent of y. So that means this guy denominator is also independent of y, right? So they can actually go outside. So cancels, right? And then this guy is actually equal to 1. Once you cancel it, then this is just a density. So this just disappears. So basically we get, right? We get equality. So that gives proof. Now here's a additional comment. Now suppose x2 is never observed. And to make life easy, let's just assume that x2 is independent of x1 and expected value of x2 is 0. That means you can actually treat this as a error term, right? Because this is what do you mean by error? Error is something that that you don't observe, essentially. So you don't observe this part. So this is another error, right? So that is been basically this is your error, and which is actually you have this one. And turns out that your error is actually independent of x1, so which is nice. And so that means you can actually have a nice property. But the problem is now this new error are correlated with x1. Sorry, no, this is actually a function of x2. Okay, so this is a function of x2, and this x2 is a part of T. So, so this is T. Because T is what? Indicator of alpha 1, right? Alpha 1 x1 plus alpha 2 x2 plus u 0, right? So that means so this guy is correlated with t because it's a function of x2. So even if you control x1, uh, this uh, this error term is correlated. So that means if you do not have access to x2 and analyze the data based on only on x and t and x1 and y, the final estimator will be biased for the causal parameter in general because you the missing and random, I mean ignorability assumption does not hold. Okay, so that is in econometrics it is called omitted variable bias. Essentially, you get bias. Okay, so that means it's very important to include all potential compounders into your model. Okay, that is the bottom line. So one key result is now that we need to assume this, right? This is NUC assumption, and then there's additional like suitable assumption, which is a consistency type of consistency measurement assumption, and positivity assumption is also needed. So under that assumption, we can show that we can show this. So this is a key identification formula. So identification means that we want to express the causal parameter. So this is a causal parameter, right? So this is because what do you mean by causal parameter? Causal parameter is a parameter that is defined using potential outcome. Using the potential outcome. So the whole problem is that whole problem with the causal inference is that we never jointly observe potential outcomes, right? We only observe one instead of two, right? We never observe these potential outcomes together. So if you remember the presentation seminar yesterday, the idea was you use a fancy machine learning, whatever, right? And the key idea is encoder, decoder, autoencoder. Encoder is nothing but learning. Okay, decoder is actually prediction learning. So that's my understanding. So encoder is basically learning, use the data to train your model, and then decoder is essentially generative. So once you have if you think about simulation, so simulation is what you specify, you give some number, right, parameter, and generate data, right? That's a simulation. But the emulation is different. Emulation is that don't use the arbitrary number. You should use the number that comes from your data. Okay, so the data supposed to come from, the number, right? The parameter should be obtained from the data that you have. So basically, if we actually have the encoding two different data, so that's my point. So you can separate the data into two parts. One is the treatment group, the other one is control group, right? And you do the learning you do this learning separately, okay, then you actually have two models, right? One is the t equal 1 model, the other one is t equal 0 model. And then once you know the parameter, then you can simulate it, right? And then once you can emulate it, then you can generate two potential outcomes, right? To whatever the future outcome or even your current data, you can actually generate two potential outcome, and then you can basically uh, say about your parameter of interest, potential outcome parameter, right? Causal parameter. That's basically the key big idea behind causal inference. And then maybe there's some additional complication. But anyway, so this identification formula is critical because basically it says that under these assumptions, right? So this kind of argument can apply if we have this assumption. If you don't have this assumption, then we cannot really say that. So okay, so under these assumptions, we can basically use the observed data, right? So this is the observation data, observed part, observed data. And and this is your potential outcome. So you can translate, you can transfer your observation to what you are interested in. Okay. I think I used this slide part in other classes, so this I will be just a quick. So Stuma means that you have a, so this guy is y1 t plus 1 minus t y0, right? So if you have a particular t, that means you only have one is 0, the other one is, your indicator function is either 1 or 0, right? Depends on what your t is. So that basically means that you end up getting that part, right? Capital T equal to small t. Okay. So that is the Stuba assumption implies. And then secondly, this guy, right? This guy is equal to because of the conditional independence, the dependence on capital T disappears. So that means you can actually have the equality here, right? So that means using the two, we can get this equal. Now we want to take the expectation both side. Okay, so we take the expectation both side, and then hope that these two expectations are equal. Usually they will be equal, right? So two, because this is a random variable. So the two random variables are equal almost everywhere, then their expectation should be the same, right? So that means we need the almost everywhere assumption, right? Used. That means we should have the same support. So that's the this assumption. So basically, if x equal to y, then expectation of it will be expectation y, right? But that's not really accurate statement because it's a probably random variable, right? So when we say two random variables are equal, what that means? That means they are equal in the sample support, right? In the support that random variables are defined. So that's basically is. Okay. So that's basically this. So this equation 3 is a key assumption to do what we want. So basically we are now in a position to do to use our training to learn the regression model and then use that to estimate the causal parameter. So originally, right? Originally, this is y1. Originally, this is our potential parameter, and then we get this. Because of 3, right? Because of the equation 3. So that means to estimate tau, all we have to do is to estimate what's inside the conditional expectation, what's inside in the expectation, which is conditional expectation. So we can write it as a function of q and t, and then use this formula. Okay. Now the problem is so basically the problem reduced to constructing this learning this conditional expectation. But there's some caveat. Okay, so how we really want to do this, right? How to complete. So basically, you want to construct you can basically have two sets, separate out two sets, t equal 0 set, t equal 1 set, and do whatever the regression, right? Non-parametric regression, whatever. Okay. But if you do non-parametric regression, then maybe course of dimensionality can happen. If X is dimension is large, then non-parametric regression is probably not feasible. So we may need some dimension reduction. So here's so rather than using full X, okay, rather than using full X, we can consider function of X, okay. So function of X. So that means X is okay. X is P is a dimension of okay. I should have. So P is the original dimension of X, okay. But I want to reduce the dimension to K. K is of course K should be less than P. And then still want to make sure that this is what we want, right? We want that the regression of y and x should be equal to equivalent to the regression of y on Rx. So Rx is a dimension reduction, but at the same time, we should not lose any other information, right? We should not lose any information. So that means it should be sufficient. Okay, so that means it is called the sufficient dimension reduction. So what does that mean? So if sufficient dimension reduction, then that means you're okay. So that means what that means. Okay, this guy is f. Okay, here's actually y given x and Rx. So suppose you condition so construct conditional distribution of y given x and Rx. But Rx is nothing but a dimension reduction of x, right? So conditioning on, so this guy should be same as this. So this is by definition, by any function, right? Any function of Rx. Any function of Rx will satisfy this. But by the definition of, on the other hand, we also said that this is, okay, sorry. So this is the surfaced debate, right? So if Rx is sufficient, then we have additional equality. Okay. So that means we have this equality. So this equality could be expressed as conditional expectation, conditional independence. Y is conditional independent of X, conditional on Rx. So Rx is enough, right? So Rx is enough. Once Rx is given, then Y, other part of X doesn't explain anything about Y. So that is interesting part. That's for the usual Y and for the usual regression context. But here we are talking about the regression of the potential outcome. So that means we want to use potential outcome. That means our sufficient statistic SDR, sufficient dimension reduction should depend on T. So that means this guy can be replaced with. Well, what is the largest dimension reduction? Largest dimension reduction is actually the conditional expectation, because why? Because yt. So if I write it as a q, right? qxt, right? So basically expectation, right? If I write it as and then the others are all just noise. So that means yt conditional on this one, right? Conditional on this one is error term, right? So conditional on this one, the y is completely determined by error, and error term is independent of x. Okay, so that means you achieve this because conditional on the conditional expectation. This is just an error, so error is independent. Of course, we don't know this conditional expectation in general. Okay, here's a very interesting point. So what am I doing, by the way? My point is that we have originally we have this one, right? So that means this one leads us to say that, okay, is this enough to compute the conditional expectation, right? And which is actually can be written as so basically missing and random, or I mean ignorability assumption leads us to estimate the so leads us to identification strategy, which is basically you have only to compute the conditional expectation. The problem is usually this could be the high level concept, right? You cannot really compute the conditional expectation for large dimension. So you may want to focus on narrow down to using this regression. So what we really want is you want to use a regression on Rx. Okay, and you utilize this one. Oops. So okay. you want to utilize oops, given because this is a difficult task. So computing the conditional expectation of y given for general x is difficult. So we want to narrow down the problem using if I know the Rx, this is dimension is low, so this regression is probably easier. The problem is that if I want to use that, right? So if I want to use that, I need a condition. So this doesn't necessarily come from this one. So what we want is that, okay, that means you need to have some sort of do you have a ignorability conditional on Rx? So that is something that we need to show before we want to apply. Okay. And the answer is that here's a lemma. So if this is true, okay, if this is true, and also this is, and also the regression, the SDR assumption 5. So SDR assumption is 5 is this one. So that means your regression, right? Your regression of YT given X is equal to so that is the basically equation 5, SDR assumption. Then we have a missing and so this ignorability condition. This is ignorability conditional on this as Rx. Okay. Let me explain this a little bit further. Okay. So what does it mean? Okay. Suppose you have X1. Suppose your model has a dependence on X1, not X2. So you have a smaller covariate. But okay. So that means your reduced model, right? Reduced outcome model. But you're missing a random. Is a full model. Sorry. MAR. No, ignorability, right? So it says essentially missing a random, but here we are not, this is not missing data course. So the ignorable or NUC, right? No measured, no unmeasured compounder. Is conditional on X. Okay, now the question is, can I use, so in that case, is it okay to use X1 only to fit a regression, right? I want to use this one, t equal t. I want to use x1 only to fit the outer model. But is it okay? Well, the answer is yes, but you need to first make sure that Michigan random force condition on x1 only, right? So because this one will imply this. So that means we need to check this condition. Okay. So that in other words, this guy, okay. So that is the lemma. So lemma basically says okay. Lemma basically says what? Right. So I guess it means this guy is equal to yt given rt x and t equal t. So this is so this conditional independence, it means this, right? So once this is verified, then you can say this is equal to this, right? So this part is a Stubauer, right? This part is so this equality comes from Stuba. Because what do you mean by Stuba? Stuba is y is a t y1 plus 1 minus t y0. Okay. So you can actually put it to here, and then given condition on t equal t, you get this. Only have this, right? So this part is Stuba. But what we really need to show is this part, which is this one. So that part needs to be shown. Okay. And here's a very simple way of proving that actually. So remember, this lemma has two assumptions. One is missing and random, right? Usual ignorant assumption. And then the other one is the SDR assumption. Okay, I'm going to use this to show this using graph. Okay. So I don't need any formula, just use graph. And then, okay, what does that mean? This graph, original. So this is the actual original graph. Okay, this original graph was, suppose you have this, original graph has a missing random, right? Ignorable. So what is the ignorable? It's a conditional independence, nothing but the conditional independence. So this conditional independence can be graphically expressed by this way, right? So that's one assumption. What's the other assumption? The other assumption was SDR assumption. SDR assumption is what? This guy. Y and X are conditionally independent given Rx. So then that is basically the other part. So this part is YT and X is conditional independent given RTX. I can write it. Okay. So given, right, given Rx, given Rx, X and Y are conditional independent. That means the original arrow break down. Okay, break down. Once you know this, okay. Once you, if you don't have this one, right, then they are correlated, they are related. But now you have additional information. This information basically explains why there is an arrow. So this arrow actually is due to this, due to existence of this one. So now that you have more information, you can actually break this arrow and construct the whole big picture. Okay. Now, what you want to show is what the goal is to show that y and yt is conditional independent of rtx. This is what you want to show. This is what you want to show. That means you conditional on Rx, there should be an arrow to T, and there should be an arrow to YT, but there should not be an arrow between Y and YT, T and YT, right? So that's exactly what it is, right? So there is an arrow to YT, and there is an arrow to T, but there is no direct arrow between the two. So that basically finishes the proof. Complete the proof, right? Okay. So I thought that's kind of interesting. So see, we have two assumptions, right? One is this one, the other one is this one. So the first assumption is a missing a random type assumption. Right? The missing a random type assumption, ignorability assumption, cannot be verified from model. But the SDR assumption can be very checked from the set. Because it's essentially, okay, how do you check your particular model is correct or not? You can do a lot of model diagnostics, right? You can use the residual plot and so make sure that your residual is independent of each component of the x variable. So things like that, right? So at least this second assumption could be checked in principle. And also there's some techniques available how to choose SDR. But I'm not going to cover that in this class. So the point is that given the surface dimension reduction function, then we can build a model. Okay, so given the surface dimension, so given the RTX, we can build a model, and that is basically outcome model approach. Okay. So so then we can basically here you have you can basically construct. So once you have that, then you basically have a parametric model, and then under the assumption that you don't have to worry about missing a random given this one, right? Because of the lemma already. So then we now we want to estimate the parameter, which is fairly straightforward. So once you have estimate the parameter, then you can plug in and then test by our estimator. And this model could be written as a two separate model. And then estimate the parameters from two different models. The same thing. Okay. So basically, it's essentially prediction, right? So nothing but we have a model, outcome regression model, and then for given the outcome regression model, we estimate the parameter, and uh, and uh, and predict. And so then the assumption is that we have a three. So this is the first three is the fundamental assumption, right? The first three assumption that is a fundamental assumption for causal inference, any causal inference with from observational study. So I guess one thing I like to say is that, okay, actually it's not really observational study. Actually, in any study, we need this experiment, these three assumptions. But the only thing is that if we do experiment, okay, then this is satisfied. Experiment, if you do experiment, then we control. So we make the design to satisfy the NUC condition already. Okay. So in the observational study, we need to assume this one, but in the experiment, we actually make it happen. So that okay. So that's basically is, and then how to do inference, statistical inference, is just a usual technique. So okay, basically, if you now this is our okay, now this is our estimator, and we want to construct the confidence interval and things like that, variance estimation. So if you do that, then that means you need to realize that there's a additional model parameter that we fit from the data, right? So this is a kind of a sometimes called the noises parameter. So tau is the parameter of interest. And gamma 0 and gamma 1 are noises parameter. So that is basically this, right? So there is estimated noises. So to reflect, we need to reflect the uncertainty of this tau hat in estimating the gamma hat in estimating the tau hat regression. So here's some. We need to use some large sample theory. Okay. So we need to. Okay, here's a basic setup. We suppose you have a random variable, IID random variable, certain distribution, and parameter characterize the features of the distribution. And then parameter of interest is defined through the following equation. So, and then and we can use massive moment. So this is the estimating equation. We can use estimating equation. So if you this kind of class sometimes called the Z estimator in the literature. Okay, and now we usually use some kind of Taylor expansion and to obtain the variance that leads to some sandwich formula. So this is sometimes called the sandwich. So C is the variance part, variance of the U, and then D is a derivative. So that's the commonly used technique, and we can use this idea to apply. And then all you have to do is estimating this C and D. So C can be estimated by mean, and then D is also estimated by sample mean. So then you can get a variance estimator. So let's use this sandwich formula and apply it to our problem. Okay. So we know this is, so we have three equations. One is the U1 is the equation for estimating tau. U2 is the equation for gamma 0. U3 is the equation for gamma 1. Okay. Because we have three parameter, that means we need the three equation. Right? So we need to solve the three unknown. There's three equations usually, right? In the linear model. And then the equation supposed to be computed from the data. So we use the data to construct the defining equation. So this is the estimating equation for gamma 0 and gamma 1. And then once you obtain this one, then you plug in and estimate tau. And then once you figure out, right, once you figure out the specific form, you can apply the unified theory. That's it. So you can view it as like a vector, right? U is just a vector of three equations. So write it that way. And then apply Taylor expansion, the sandwich formula. That means you need to do some sort of differentiation. So I will not cover the details, but this is pretty much straightforward. So basically, this guy is you have a right. You have a U1, U2, U3, and you have parameters tau 1, tau as gamma 1, gamma 0, gamma 1, right? Then you know how to compute. Okay. So that means, and then you do some, that means you need to compute the differentiation, I mean, inverse of the matrix and simplify, and then you end up getting something like this. And which end of the day you will get, so that means you get, okay. Nice thing about this one is that your tau given you. So this is free of, okay, U2 and U3 has nothing to do with the tau. So when you compute this guy, right? When you compute this guy D, you can actually achieve some simplification because you only care about tau. So you have some simplification. So end of the day you get this one. Where is that? Okay, right. Yeah. I think that's all, I guess. So once you obtain this, linearization, right? So once you obtain this linearization, all you have to do is plug in these unknown parameters. Just apply the plugin estimator and compute the variance estimator. So this is typical linearization. Hopefully that you can compute from the data. So I think that's probably all for today, I guess. But there's some, when it comes to actual computation, there's some details, but I think so, so just algebra, a lot of algebra. But the big picture should be is just the Taylor expansion and sandwich problem. Okay, I think that's all for today. Any questions? Okay, well, so this Thursday, day after tomorrow, we don't meet here. We'll meet online. So I will hope to see you at 8, and we'll have a Zoom class this Thursday. Okay.